STM32N6 is the first ST microcontroller to integrate what is called a neural processing unit. And we will focus on this IP in this session. So the agenda is the following. We will first review how the neural art is integrated within the STM32N6 architecture. Then we will see how a given neural art is processed internally. And we will go into the neural art internal mechanisms to understand really what is done inside, and also to understand the output of the tool that will help you that will accompany you into integrate the integration of a neural network in the on the hardware. Then we will detail the compiler itself. So the compiler is called the STH AI tool. It's provided by ST. It allows to pre-process, to convert and compile a neural network to be processed then and understood by the neural art IP. And then we will have a demo session. So it's not really hands-on because you are not supposed to follow it, because there are some steps that are quite long. There are some command line to types, but you will get all the material to redo it afterwards in the slide set. So here it will only be a demo part, but you can do it afterwards on your own. And before I will start this demo, and we'll have a short break to breathe a little with all these informations. So how the neural art, how does it fit? What is it first, and how does it fit into the STM32N6 architecture? So what is the neural art? So it's an ST in-house neural processing unit. So it's a reconfigurable convolutional neural network inference engine, and it runs at 1 GHz. So what is a convolutional neural network? It's a neural network first, but it's a very complex one, since it processes images. And so we will see later in the slide set, it has some additional steps that will be also accelerated in hardware in this case. So convolutional network, I would say, is more than neural network. So it means that the neural art is able to process a regular neural network as well. So the NPU is provides some hardware support for main of the convolutional neural network inference operation. We will come to that. And it has the constraint of being an integer-only hardware IP. So it supports 8-bit quantized model, weights, and activation. In terms of integration, the neural art is sharing the memory, the power, and the clock system of the N6 microcontroller. But we said that in the next slides, it has a dedicated high-speed memory bus to some of the SRAMs, and that was one of the questions in the chat, so I will try to answer that. And it has some control interface as well, so it can be scheduled by the Cortex, so Cortex driven. So then the Cortex is using the neural art as a side IP to delegate the inference operation to it. But it can also be self-driven thanks to an internal scheduler. So you can just set input and output, and all the steps, all the intermediate steps will be done in hardware. And it comes, of course, it's not really a microcontroller integration, but in terms of ecosystem, it comes with software programming tools, and we will come to that, notably regarding the compiling tool. So consider the NPU as, I don't know if you are aware of GPU. So GPU is a graphical processing unit. So It's usually useful for graphical user interface acceleration, but it's not handling on its own graphical user interface. The Cortex delegates some tasks, some pixel processing tasks, to a GPU. The same way, the processor will delegate inference tasks to the neural processing unit. So here is a simplified version of the STM32N6 architecture. So basically, the Cortex M55 running at 800 megahertz is accessing 2 megabytes of internal RAM, so SRAM 1 and SRAM 2, through a 4 megahertz bus, and is also able to access, of course, external RAM and external flash using the same bus. The same way, you have other masters on this 4 megahertz bus, so the DSM-IPP, we will come to that with my colleague, the LTDC for the control, the display, the LCD controller, the GPU 2D, so the graphic accelerator. The DMA2D is also a graphic accelerator, and other like H.264 video encoder, and even motion JPEG, which is not. It's in this diagram. So here it's a regular way. We have one main bus, and all the masters, including the Cortex, are accessing it. Regarding the N6, it's a bit different. There is a kind of private garden for the neural art. So the neural art here has its own bus running at 900 megahertz, and on which it can access. It has a privileged access in terms of throughput and access time to these 4 blocks of internal RAM, so SRAM 3 to 6. And it has also a cache available to access the main bus. So the neural art, you can see here, has some privileged access to part of this 4.2 megabyte of internal RAM that is available on the N6. It's not totally private, of course, because there are some bridges. There is a bridge here. So the Cortex is also able to access this SRAM 3 to 6, but with the penalty of this link. And the same for the other components. So the target here is to give the neural art the highest throughput and highest and smallest access time to a specific area of SRAM to improve the performance of the inference, because the neural art will do many accesses to RAM to read the input weights and to write the output, so to process a convolutional neural network. Another way to visualize this is in this subsystem, the subsystem overview. So it's a bit, okay, you will take time to look at it. The important point is that here you have the private garden of the neural art, so 32 gigabytes per second to access the SRAM 3 to 6. And you can see that as soon as you go to the other external not external, internal RAM, or in the other internal RAM, you are dropping to 12.8 gigabytes per second. So even with some cache, we encourage you to use this as RAM for the neural network processing, if you can. So that's why we were talking in the chat about maximum definition. When you go to high definition, for example, 6 VGA definition for the neural network input, you will have to somehow use this internal RAM that are external to the private garden of the NPU. And then you will have some penalty, and strong penalty, on inference time. And it will be even higher if you go to external RAM, then you will drop down to the 0.8 gigabyte per second, because you will have to go to 200 megahertz. So, okay, yes, in theory you can use up to let's say 5 megapixel sensor input to the neural network. In practice, first, a given neural network will usually not run with not process these high definition images, because it means an infinite time for the training as well. So it will be a reduced size for the image definition. And why? Because it will increase a lot the inference time, which is not the purpose, even on a high performance NPU. So that's another way to show why there is this privileged domain. So we can see here I'm doing some name dropping here. We see high throughput, low latency, so that's the best case. And when we go to external flash or RAM, we have a low throughput and high latency. And so this naming will be I will mention again this naming. So just keep in mind that throughput and latency is a characteristic of the memory that we will give the neural art at compilation time. That is a very important topic. So let's go now deeper in the neural art IP. So it's not the first IP in this case in the ST family. Usually, the IP such as graphic accelerator, notably, have several names. The reason is that you have the IP name itself, and then you have the commercial name. It's the same for the neural art. So why I'm mentioning this is that because you will see Aton sometimes in the API or in the documentation as well. So Aton is the name of the hardware IP. The neural art is the name of the neural processing unit solution. So it's the same when you talk about when we talk in the documentation about neural art or Aton, it's the same item. So here we are introducing the notion of Aton epoch. What is an Aton epoch? So first, the neural art cannot process a convolutional neural network as is. You just not put your TF-Lite model and it will run inference on it. No, well, TF-Lite, yes, but not any model. So TF-Lite, because it needs to be 8-bit quantized. So a TF-Lite model is quantized usually. But that's not the only requirement. So I told you that the hardware IP is processing 8-bit integer inside. So yes, it needs a 8-bit quantized neural network model, but this neural network model needs also to be pre-processed. And the pre-processing will result in splitting this neural network model into elementary subsets that are named Aton epochs. And these epochs will then be sequentially executed by the Cortex M55 or by the neural art using its internal scheduler. An epoch is there is no hardware state concert between two epochs execution. A given epoch will configure the hardware, the neural art, execute, and then the neural art will process the next epoch, but without any information on what has been done before, except the output of the previous epoch. And this output is stored in the memory subsystem. Just one thing to mention here is that the epoch is not related to epoch notion in neural network training domain. Just a reminder for those of you who are used to work with neural network. An epoch in neural network training model is not it's the same word, but it's a totally different item. So what is an Aton epoch? So what kind of Aton epoch are available? So here on the right side, you can see the output of the compiler that must be run on a given neural network before using it on the STM32N6. And you can see this example, so it's the one we will use in the lab. It generates 21 epochs, and here is the type of the epoch. So there are 4 types of epochs. The first one is a hardware epoch. So it means that all the operation of this epoch, this elementary operation, will be fully mapped on the NPU hardware resources. And it will be scheduled by the cortex. Another depending on the neural network, there can be some operations that are not supported by the neural art. And in this case, it will generate a software epoch. So still scheduled by the host, but also executed by the host, so by the cortex. Then you can have a hybrid or extra epoch. So it's a mix of hardware and software operations. So it will use the cortex not only as a scheduler, but also as a processor. And some subpart will be used using the neural art hardware operation. And finally, there is the meta epoch. So it's the case in this one. So it needs a specific configuration of the compiler, saying that we want to use the meta epoch, the internal epoch controller. In this case, it's a hardware epoch, so it's like the first one, but instead of being scheduled by the host, it will be scheduled by the neural art itself. So it can be interesting to have a mode where you are still performing some inference on the subsystem where in low power mode, where the cortex is not running at full speed, maybe, and but still the neural art will be able to perform some inference on its own by sequentially executing the epochs of a given neural network. So I hope I have not lost all of you. We have to go a bit deeper again to understand again the output of this compiler. And the more you know, the more name dropping I do, the better it will be for you to understand what is the output and how to do some customization or some optimization on a given neural network. So here it's a visualization. It's a part of a neural network visualized using the Neutron tool. So it's a tool that is public that will provide as well in our ecosystem. I'll give you the link at the end of this presentation. So you can see here some operation that must be performed so it's not the start of the network and the end. It's just a subpart of the neural network. What the compiler will do is to split this neural network into epoch. So into operation that will be understood by the hardware, the neural art. So for example, this part will be an epoch 2. Again, epoch 2 because this is not the beginning of the start of the neural network. This part will be the epoch 3, and this part will be epoch 4. And for each epoch, you will have some input parameter, input data, and output data that will be given to the next epoch, and etc. And so that's data, and you have also some parameters that are specific to your neural network, so that will be input as well to each epoch. So let's have just a quick reminder of what is a convolutional neural network. Don't be afraid, we will not go deeper than this. The idea here is to introduce you to do some name dropping, like these pink names, pink operations. So what is a convolutional neural network in terms of inference? What does it mean? So on a given input image, it will do some convolutional and pooling. So convolution is basically what is called a feature extraction, so convolution and pooling. So it will browse the input image using a sliding window, basically. I will not go deeper in that, but it's just to give you an idea of the amount of processing that is needed just to perform an inference on a given image. So this sliding window is the convolution, and the pooling will be there to it's an operation to extract and highlight the important information. So it will remove some pixels, and maintain and highlighting important information. So that's what is basically the pooling. And after that, we'll have a fully connected layer, so that this is a more regular neural network as we are used to be presented to. So the operations that are between these two feature extraction and classification steps are pooling. So these are operations, convolutions, activation functions. And here we have basic multiplication, addition, and activation function as well. And so what does it mean in terms of neural network internal structure? So in the processing unit that are inside, this is exactly, in fact, what we find in the internal processing unit. So the neural network is composed of several processing units, and a processing unit. So here it's a very basic example of what can be an epoch. So you have here 6 processing units. You have a convolution processing unit and activation processing unit, so to apply some activation function and perform some convolution. So these are computation activation unit. Then you have streaming engine processing unit. So this is only a connector between the two, and between these two processing units. And finally, you have other processing unit called also streaming engine, but to access memory. So with a DMA inside, to read the data from the previous epoch and the input parameter for this given epoch, and to output to the memory. So this processing unit in the neural art are listed here. So again, it's just a name dropping, so you are not supposed to really manipulate this processing unit yourself. It will be done automatically. But the idea here is to also understand that there could be limitation on a given neural network that will not be fully implemented in hardware. And why? Because there are some specific processing units, and mostly computational one, that have been selected, and others that have not been selected. So we can see that we have two pooling units, two activation units, some arithmetic units, so for addition, multiplication, subtraction, etc., and affine transformation, and some more connection unit for the stream engine. So these are all the bricks that the compiler will use to build each epochs during the compilation. So we will not go deeper into this neural art. The idea was first to help you understand the output of the compiler, and also to show you that the neural alert is not fully a black box. It has some. We give the visibility to what is inside, and so that you can understand the potential limitations. Each time you will see at the bottom in yellow, you will see the links to the corresponding documentation on st.com or on the wiki pages. So I've been talking a lot about compiling a compiler and so the pre-processing of a given neural network. So let's go deeper now in this topic. So for practical reason and better understanding, we will consider the command line version of the tool. So the tool is called the STH AI tool. So this is how you call it. So it can be, of course, in scripts, but if you call it manually, that's what I will do during the lab. This is the command line. And what is behind is that, so as input, you give a TF-Lite model, so a quantized model, so either in TF-Lite format or in ONNX format. And the other input is a memory pool description and an add-on compiler options. And so now let's remember what I mentioned during the integration, the neural alert integration slides. I talked about high throughput and high on low latency, depending on which SRAM you're using or is available. This will be defined in the memory pool description file. So to the compiler, the ST compiler, you will provide a model, a quantized model, and a list of memory areas that are available that it can use to perform to create the epochs, because you may want to save some memory for other purpose. Then you will have to limit and not give all the 4.2 megabytes to the neural alert processing. So it will compile these two information as well as some specific compiler option. For example, I want to use the Epoch controller, so I want the neural alert to be kind of autonomous or not. So there are also some add-on compiler options that are described in documentation. The output of that will be a report file. So the report files will contain the list of epochs that have been generated and some as well some memory usage information, and it will give a .c file, which will be the NPU configuration, the neural alert configuration, using the add-on API, and a memory initializer, which will be how the input weights and activation function of a given neural network will be organized in memory and processed to be processed by the neural alert. I was hiding this part because, in fact, you will see also in the output files there is an intermediate representation of the input model in ONNX format that it can be used for debug and for optimization as well. So this STH AI tool will call inside a NPU compiler. So it means a lot of intermediate processing, internal processing, that will be also part of the output. We will see that in the lab. So again, all this is available, described in the documentation. Let's come back to this input memory pool description. You can see that I was talking about throughput and latency. Here it's an example of a memory pool, an mpool file. So you will provide, okay, the compiler will able to use the XE SRAM 5, 6, which has a high throughput and low latency, and as well as the an Octo XPI external RAM with a mid throughput and high latency. So the tool will automatically do the best combination of this memory to store and to prepare the output memory file for a given neural network.